welcome to Nano Explorations, a community outreach to a student webinar designed to help you engage with the MIT community and the nanoscience, nanotechnology innovations, and other advanced research areas happening at MIT. Today, it's my pleasure to introduce Skylar Deckoff-Jones, who is a doctoral candidate in the Department of Material Science and Engineering. I'll be your host for today, Brian Anthony. I'm the Associate Director of MIT.nano. Skylar's talk, my apologies, will be on 2D materials-enabled multifunction midIR optoelectronics. Please hold your questions till the end. We'll take questions either if you directly type into the chat or if you can raise your hand, and I'll take the questions in the order that they come. So Skylar, please take it away. And I also will comment that unfortunately, given Skylar's computer, you won't be able to see him at the same time you see his slides. So before you go live, Skylar, just make sure that everybody wave and say hello.
Awesome, perfect. Thank you for the introduction. Hello, everybody. Thanks for coming to my talk. I'm broadcasting right now from a tiny apartment in Paris. So it's great to feel connected to the MIT community and get to share my research. So now I'm going to share my screen so that you guys can see my slides. So I am a fourth-year PhD candidate from Professor J.J. Hu's group, and my research primarily focuses on using two-dimensional materials to realize new high-performance optoelectronic devices on integrated photonic platforms. And a lot of this work, I'm presenting a broad range of the research that we've done as a group across many collaborators, but the main focus is from our collaborators from Professor Wenjo's group at Purdue University. And I'll point out exactly when their work comes in. So I guess the first question is to motivate why we care about the mid-infrared for applications in integrated photonics. And there's three primary applications being chemical sensing, free space communications, and thermal imaging. On the figure to the right, we see the motivation for chemical sensing. So many molecules show very specific absorption spectra in the mid-infrared, which is often called the fingerprint region. So this can be great for sensing of pharmaceutical drugs or other various sensing applications. However, the mid-infrared also comes with its own set of challenges, being finding appropriate materials that are both transparent if you want to guide light in the mid-infrared, say in a waveguide, or materials that have appropriately small band gaps if you want to create active devices in the mid-infrared as well. And that's where my work sort of focuses on. So first, to outline the talk, I'm first going to introduce chalcogenide glasses, which are the transparent waveguiding material that we've used, and also motivate why these are a great material, as well as the chalcogenide glass on 2D material platform that we've developed. I'm then going to go into a number of different devices that we've prototyped and talk about their various merits for applications in the mid-infrared, both for photo detection and modulation. So first, to motivate the chalcogenide glasses, as well as 2D materials. So for those of you who aren't already on the 2D material hype train, 2D materials offer a number of very appealing properties for photonic applications. So in this figure, we see, this is just four very popular 2D materials. I'm sure all of you have heard of graphene, but as well as hexagonal boron nitride, MOS2, and black phosphorus. And we see that from these materials, we span a huge portion of the electromagnetic spectrum through their various band gaps. So we have very large band gaps to the zero band gap of graphene. So there's a large tunability. However, within each material, you also have additional tunability by controlling the thickness. So traditionally, a 2D material is a single layer, but oftentimes within the 2D materials communities, you're looking at few layer thicknesses or even approaching tens of nanometers to hundreds of nanometers, in which case you're transitioning to that bulk regime. And through the control of the thickness, you get an additional handle to tune the size of the band gap. So this is really promising for light emission and detection, However, the 2D materials, because there's a large array of them, have demonstrated other great properties for optical nonlinearities, various modulations, septuple absorption, even magnetic properties as of recently. And they already have been applied to a lot of integrated photonic devices. However, traditionally, it's done by transferring them onto existingly fabricated integrated photonic devices. So for example, if you start with a silicon waveguide and say some patterned metal contacts, you can then, in this example above, transfer a layer on top of your waveguide and contact to make, say, a modulator. However, this comes with a number of downsides. For example, as you can imagine, you now are transferring a planar material to a non-planar surface, which can result in stresses and strains and potential ruptures in the 2D material. Additionally, you're limited to the 2D material being on the top of the waveguide, which means you're only going to have weak evanescent interaction. And also, scaling this up for high throughput on wafer scale systems is potentially difficult. So we propose a monolithic system where we can envision, rather than transferring the 2D material on top, we start with a substrate with an already existing 2D layer and then somehow fabricate the waveguide and contacts on top of the 2D material, which would allow higher throughput and other particular advantages, as well as alignment accuracy, which we'll see in the examples, which I'll talk about soon. And when it comes to the light guiding medium, chalcogenide glasses, which are glasses comprised of the chalcogen atoms, sulfur, selenium, and tellurium, offer a very preferable material system for creating waveguides in the mid-infrared. So the chalcogenide glasses are already quite popular and available commercially in the form of lenses and fibers, and perhaps most famously for rewritable phase change CDs. However, they also show great promise for integration with 2D materials. So here we have the band gaps of a variety of 2D materials, and then we have the transparency window of the chalcogenide glasses. And so we see that we can envision using this chalcogenide glass as a waveguiding material for various active devices based on the 2D materials. However, another key advantage of the chalcogenide glasses is their epitaxy-free and low temperature deposition. So this is really what enables us to create waveguides on top of the 2D materials. They can be deposited on substrates at room temperature without actually heating the sample. So you don't need to worry about damaging the oftentimes fragile or reactive 2D material beneath. Additionally, our group in the past has demonstrated very high quality waveguides with very large quality factors. So you won't be sacrificing the quality of your waveguide as well. And finally, you have tailorable optical properties. So there's a wide range of chalcogenide glasses of different compositions. So you can tune your refractive index and your transparency windows by choosing the appropriate chalcogenide glass. So with this platform in mind, I'm gonna jump into our work on modulators and photodetectors based on both graphene and black phosphorus. So first, I want to give some background as to sort of show my previous comment that the chalcogenide glasses can be deposited on 2D materials without damage. So on the left, we have a Raman spectra of graphene with and without our chalcogenide glass. And we see that after deposition of our chalcogenide glass, we don't see a appearance of a defect peak. So we see the Raman spectra is still preserved. And additionally, further, we look at the mobility and carrier concentration of graphene with 4 different samples. So one just on silicon dioxide, one with the chalcogenide glass just on top, one with the chalcogenide glass just on bottom, and then one that's sandwiched in the chalcogenide glass. And impressively, across all the samples, although we do see a change in the carrier concentration, we don't see a change in the mobility, which is, it's very common, for example, when you deposit other dielectrics, that you get a degradation in the mobility of graphene. So this is an achievement which can be attributed to likely the low thermal budget and low deposition temperatures of the chalcogenide glasses. We also look at the Raman spectra on a variety of other two-dimensional materials. From this, those who are familiar with 2D materials know that black phosphorus is a particularly reactive 2D material, but we see no change in the Raman spectra of the black phosphorus, as well as the other two-dimensional, as well as a number of other two-dimensional materials. And furthermore, we look at actually using the chalcogenide glass as a passivation layer. So because black phosphorus is quite reactive, it oxidizes very easily. However, if we put chalcogenide glass on top of a flake of black phosphorus, we see that it can actually prevent the black phosphorus's oxidation and damage, even from a thin layer. So ultimately, the chalcogenide glass is a very appealing material, not only as a light guiding medium, but also for passivation as well as use as a gate dielectric. And to ultimately summarize sort of our fabrication method, this figure schematic shows the method. So as opposed to the method previously where the final stage was depositing the 2D material, we start with the substrate with graphene, and we're then able to pattern electrodes, the graphene or 2D material itself, and then finally the waveguides. And to show the merits of this method, I showed you the first device which I'm going to be discussing today, which is a graphene-based mid-infrared waveguide modulator. So the mechanism of this modulator, on the left you can see a schematic, and on the right is an SEM image of the cross-section of the device. We have 2 layers of graphene. So we have a bottom layer of graphene, and then we deposit a thin layer of chalcogenide glass as using it as a gate dielectric, followed by an additional layer of graphene, and then the remainder of the chalcogenide glass to form the finished waveguide. And when we see that when we apply no bias, the Fermi levels of our graphene are tuned such that we get no absorption. And then by applying an appropriate bias, we tune the Fermi level so that we can then absorb photons of the centrally located layer of graphene. So not only does this enable this, this structure, but the chalcogenide glass also has slightly stronger interaction with the graphene, as it's not just on the very surface of the waveguide. And this shows the experimental and theoretical modulation depth for this modulator. And we see that we have quite good broadband modulation over nearly 500 nanometers of the mid-infrared spectrum. Additionally, we fabricated a mid-infrared photodetector where we had a photovoltaic detection response, and we see very high responsivities over a large bandwidth, where we see a decreasing responsivity which can be attributed to polyblocking, where the lower wavelengths no longer have sufficiently large energies relative to the position of the Fermi level of the graphene. And next, I want to introduce our work on black phosphorus-based mid-infrared photodetectors as well. So similarly to the graphene, where we were able to start with a layer of graphene and then alternate layers of glass and graphene, black phosphorus is, for those of you who aren't familiar with it, is an interesting 2D material because it shows strong in-plane anisotropy. So you actually have these preferential armchair and zigzag directions where you have very different properties with regards to absorption coefficients and mobilities. And so you can envision that it's actually very important to know the orientation of a waveguide integrated photodetector relative to the crystalline orientation of the black phosphorus. And so what we can do is we can start with a flake of black phosphorus and then characterize its orientation through polarized Raman spectroscopy. So this has been sort of developed over the years as a method of determining the crystalline orientation of the black phosphorus. And then once we know the orientation of this exfoliated flake, so it's a small micron scale flake, we can then very sensitively pattern both the electrodes and waveguides along the flake. And we can even create multiple devices along both directions of the black phosphorus flake to then be able to compare performance of the photodetectors along the armchair and zigzag directions. So here is a optical microscope image of one of the actual fabricated devices. So we have a number of different devices here. There's actually 6 devices where these are the metal contacts, and then in between them, these are the waveguides. And so on this particular flake, we're comparing this waveguide with this waveguide along the armchair and zigzag directions. I forgot to note that also, because of black phosphorus's reactivity so that we could measure the devices over a longer period of time, in addition to the waveguides, we also deposited a thin 30 nanometer layer of chalcogenide glass over the entire sample to improve the lifetime of the devices so that they didn't degrade too quickly. And from this, we're able to now compare the photo response of the photodetectors along the armchair and zigzag direction. If you look at the scale of the responsivity, we actually have just about an order of magnitude improvements in the responsivity of devices oriented along the armchair direction, which is quite nice. And if you look at the theory of the physical properties of black phosphorus, this actually ends up making quite a bit of sense when you account for the differences in both the mobility and the optical absorption anisotropy in the black phosphorus. So after looking at those 2 devices, there's a number of downsides to both graphene and black phosphorus. So as we see, black phosphorus is very reactive. The problem for graphene, which I didn't go into too much detail with its use as a photodetector, is because of its 0 band gap, we have high dark currents. So even when there's no light exposed, because graphene is always a conductor, you have high dark currents, which ultimately damage the noise equivalent power, like the minimum detectable signal that the sensitivity of your photodetector. So if we had another material that combined the small band gap of black phosphorus, I think I also forgot, black phosphorus has a band gap of 0.3 electron volts. So if we had another material that had both the small band gap of black phosphorus as well as was more stable and less reactive, that would be great. And that's where we've been quite excited with tellurene. So now I'm going to introduce you to potentially one of the hotter new 2D materials on the block. It's interesting because it's not actually a 2-dimensional material. So normally the 2-dimensional materials are covalently bonded in one plane and then separated by van der Waals forces along a C axis or a C direction. However, for the tellurene, it's actually these 1D covalently bonded chains of tellurium. And however, our collaborators at Purdue have recently developed a solution processing way of creating essentially 2D sheets of the tellurene. So they're able to produce flakes, which are sort of trapezoidal in shape, of the tellurene that have micron dimensions. So the scale bar is, I think, 10 microns. So you see micron lateral dimensions. However, the thicknesses they can control down to under a nanometer. So they have control of under a nanometer up to over 100 nanometers. So you have a sort of a pseudo 2D material with quite nice properties, such as a similarly small 0.3 electron volt band gap, similar to black phosphorus. However, additionally, you also see great stability. So on the left, we see the band structure of the tellurene, and on the right, we see a transistor device that our collaborators fabricated, and they measured the device performance of an unpassivated device over the course of a couple months, and they see very little change, which is quite promising for its stability. Additionally, you do have tunability of the band gap. Again, when you go very thin, you get an increase in the band gap. And similarly, you also have very nice mobilities, making it a very promising material for applications for integrated photonic optoelectronic devices. However, another very appealing thing of the tellurium, the tellurene, is its potential for scalable production or scalable manufacturing. So because it's solution processed, it's quite easy to actually coat a large wafer, and even the type of wafer doesn't matter because you're not worried about, and again, you're not worried about epitaxial growth. So here you see that they cover an entire silicon wafer as well as a PET wafer. And you do see that there's sort of this random mismatch distribution of flakes. And they do have a lot of different thicknesses and orientations, but the group is making, Professor Wenzo's group is now making great progress in being able to control the orientation as well as the thickness. So having a small standard deviation in the thicknesses of the flakes, as well as having them uniformly oriented along preferential directions. And additionally, you can also etch the tellurium as needed for, in this case, they're looking at, again, transistors from its usual sort of trapezoidal shape. So there has been some work as of recently on mid-infrared photodetectors already based on tellurene. They've been limited beyond our work to free space detectors though. So they're exciting from out of plane and then collecting in plane of the material. But already from the free space detectors, we see very impressive performances with low noise equivalent powers, so very sensitive photodetectors. However, as is often the case, when you move towards waveguide integrated devices, you see a large improvement in the performance of the device. You're able to greatly improve the quantum efficiency and collect much more light. So here we envision a new architecture for integrating the tellurium in a waveguide integrated photodetector. So we have, in this structure, we have the tellurium, which is our sort of our gray trapezoid, with a chalcogenide glass waveguide, the blue waveguide on top of it, as well as source and drain electrodes. However, we were thinking that we can further improve the device performance by also including a graphene gate. So we can have graphene, which can act as a transparent gate material in the mid-infrared, as well as a gate contact, and again, using our chalcogenide glass as a gate dielectric. So this would allow us to control the carrier concentration in the tellurene, which will lead to further improvements in the device performance, which can be illustrated here. So on the left, we do simulations to show that the tellurene has, because of its high optical absorption, can very strongly absorb the optical mode, giving it a very high quantum efficiency. Additionally, because it's so thin, or we have the ability to control it to be quite thin, we see very little scattering at the interface between the photodetector and the waveguide due to mode mismatch, so giving us very high quantum efficiencies. We then look at what is the performance of our photodetector if we vary the thickness of the tellurene. We only go to 10 nanometers because below 10 nanometers, we start to see an increase in the band gap, and we want to keep our device as a mid-infrared photodetector. So we're looking at 3 micron wavelength incident light. And as we go to thinner thicknesses of tellurene with the graphene gate, we can more completely deplete the tellurene. So it's the Fermi level is tuned closer to the intrinsic level of the tellurene. However, when we go thinner, we also get a decrease in the quantum efficiency. So we have less material to absorb the light. So there's a trade-off. And similarly, when we increase the detector length, so increase the length of the tellurium, we have higher quantum efficiency at the expense of a larger dark current. So even when we're tuned to intrinsic, because it's a small bandgap semiconductor, we still have a substantial number of free carriers. And so we still have a significant dark current. But we see with these parameters, we can get an optimal device performance for thinner flakes, 10 nanometers, with short, small devices around 7.5 microns long. And the most impressive thing is we see very, very low noise equivalent powers, which are a couple orders of magnitude better than existing photodetectors based on 3.5 materials. However, the excitement of tellurene doesn't end at photodetectors. We realized that tellurene offers promise for electro-optic modulators at wavelengths above its band gap, so at wavelengths longer than the 0.3 microns. And that's through the Pockels effect. So this is actually second harmonic generation measurements of the tellurene. So on the left, we have an image of the reflected fundamental as it's scanned across our tellurene flakes. And so we see like all the various trapezoids and some long spindles of the tellurene, all with similar intensity. However, then when we collect just the second harmonic generation, one, we get very strong second harmonic generation signal, which is actually quite stronger than the other 2D materials we measured, and even 100 times larger than lithium niobate. But we also see that when our light's polarized along this direction, I guess horizontally on my screen, we see only certain flakes light up. And when we change the polarization along the other direction, the other flakes light up. So this has to do with the strong anisotropy in that chain-like structure of the tellurium. And so we can model and experimentally measure the second harmonic generation as a function of the orientation. And from this, we now know if we wanted to create an electro-optic modulator, how would we want to orient our electric field to achieve the largest Pockels electro-optic response in our material. And so we want our electric field to be perpendicular to the length of our trapezoids. You can determine the exact crystalline orientation of these trapezoids through Raman spectroscopy, but we found that quite uniformly the chains run along this direction of the trapezoids across, as the shapes are quite uniform for many of the flakes. So with this in mind, we can then set out to design our Pockels modulator and again optimize its performance. So in the top left, we see the electric field in our tellurene as well as the optical mode overlap, which determines our confinement factor of our mode in our tellurene, and in which we can ultimately calculate our V pi L, which is a good figure of merit for a lot of Pockels effect-based modulators. And similarly, as you increase the tellurene thickness, you do see an increase in the confinement factor, which gives you a lower V pi L and better performance. Again, however, with the trade-off. So another figure of merit for modulators is often the energy per bit. So you want to be able to encode information at very low energy costs. And as we increase the thickness of our tellurene, we also see a larger resistive power consumption. And so by going to thinner thicknesses, we have less energy at the expense of weaker modulation. So again, there's this interesting trade-off between the modulation efficiency and the energy and its thickness. But we see, interestingly, that at intermediate thicknesses of around 40 nanometers to 30 nanometers, we see optimal performance at very low energies of 12 picojoules per bit and modulation speeds of 70 gigahertz. And again, this is for a particular architecture using a ring resonator, but by going to Mach senders, we can go to higher frequencies at the expense of the energy per bit. So finally, I want to summarize. I've shown you a lot of different devices with impressive performances, but I think we're most excited about the tellurene now because it shows a lot of advantages over graphene and black phosphorus, from its stability as well as its small band gap, and perhaps most excitingly is its promise for a simple approach towards wafer scale processing. So with that, I'll conclude the talk and I'll take any questions.
Skylar, thank you very much. I send the virtual and physical clap here. So please, participants, please raise your hands or direct a question in the chat. While we're waiting for some of the audience, I do have a follow-up question in terms of, as you look at these different materials, and I think your last slide maybe summarizes it a little bit, but as you project the scale up in terms of the manufacturability as it relates to device sensitivity, like do you see different opportunities for the true scale up as it relates to making repeatable devices in large scale?
Yeah. So, I mean, clearly graphene has had the most time to develop, and its production at a large scale is quite impressive at this point. So it's sort of large steps ahead of the other 2D materials, but I think largely it has that advantage just due to popularity. So if another material can be demonstrated to have physical material properties which warrant the additional research towards like that large scale processing and manufacturing, then that's quite promising, or could be promising. Again, because graphene does have its limitations, as for the example of photodetectors, and its lack of a band gap is definitely problematic. But yeah, scaling up is always a challenge, especially with 2D materials.
I appreciate that. Understood. Thank you. So let's see. Please, if you have questions, please raise your hands, or feel free to type them directly into the chat. And in terms of, as you look at the different application spaces in terms of sensors or data communication, what are the areas that you see as that maybe you personally are most excited by, but you think have the largest opportunity for impact?
Yeah, well, so I might be biased because of the research that our group and Professor Kimmerling's group does, but we have a lot of students and a lot of research that's going towards sensing. And so I think sensing is definitely a very exciting area to envision having a spectrometer that can fit on a single chip for various, like the potential applications are numerous. I think there's our group has been working with industry, various industrial applications for like sensing and fish samples or pharmaceutical sampling. So I think that's like a really exciting area that might have sort of a revolutionary impact on how we're able to detect chemicals in our environment. There's also, in the mid-infrared, there's a lot of military applications as well for imaging and applications of those kinds. So there's definitely funding that is pushing towards more research in mid-infrared.
Very good. There's a question here from Jordan. Actually, he raised his hand. So Jordan, if I can ask you to unmute yourself. And Skylar, you might want to stop sharing so we can see you when you're speaking as well, please.
Hi, Skylar.
Jordan. Okay, great.
Great talk. I've got one or two questions. So indeed, the noise equivalent power for the tellurene detectors is super duper low. So the first thing that I would think of for such a low noise equivalent power is maybe there's like some charge trapping phenomenon, which is giving rise to photoconductive gain. Do you think that's possible? And have you done like device speed measurements, which might like reveal what's going on at the electron level?
Yeah, so this noise equivalent power is actually calculated. It's not measuring a noise equivalent power that low. We're doing it through calculations. So ultimately, like factoring in different noise contributions, I was limited by the Johnson noise, which is primarily determined by the temperature, but we were doing it at room temperature, and the shunt resistance of the device. And so that low noise equivalent power was calculated assuming the gating with the graphene to achieve that low of a value. In reality, in a fabricated device, as you say, a number of other phenomenon might occur that might hamper how low of a noise equivalent power you actually achieve.
Okay, and also I'm just curious, how are the chalcogenide glasses as dielectrics? Do they make good dielectrics?
Not the best. I mean, yes and no. It depends exactly on what you're doing. Like I wouldn't recommend, you're not going to want to fabricate high performance transistors using chalcogenide glass dielectrics, but given their optical properties, for example, in the modulator that we created, they're quite good. They do have lower breakdown voltages, so you do have to be careful.
Okay. Thank you.
Yeah. Thank you. So I have a question here from Vladimir Bulovic. What is the stability or durability of fabricated structures? The parenthetical question is, what kind of encapsulation would be needed to maintain device stability?
Yeah, that's a great question. So for the black phosphorus, we used the 30 nanometers of chalcogenide glass to sort of passivate the sample. And this made the device performance was uniform over the course of days. I think I measured it like a week later, and I saw very slight degradation. But then I also measured the device a couple months later, and the performance was greatly degraded. So even with the I mean, black phosphorus is a material that degrades over the course of hours, though. So it's very reactive. So for black phosphorus, there is a large area of research that people are just trying to figure out what's the best way to encapsulate it and protect it and passivate it. On the other side of things, for the tellurium, as has been demonstrated, it's far more stable, and it seems like at least over the course of a couple months, its performance doesn't degrade, which makes it, that's largely why it's as appealing as it is to us.
Very good, thank you. So Skylar, I'm gonna send my virtual clap along again, so thank you very much, and
Thank you.
wonderful talk, wonderful work, and hope you're able to continue in this very unusual time we find ourselves to continue to be successful in the work that you're doing. So participants, thank you very much for attending. I wanted to invite you back to the same time, probably similar channel, on Tuesday at 11 a.m. For our next Nano Explorations talk, and that will be by Justin Tony Hu, a PhD candidate in electrical engineering and computer science. His topic will be on hybridized magnons in van der Waals, antiferromagnetic, and circuit quantum electrodynamics. So please join us on Tuesday at the same time. But until then, thank you everybody, and have a good remainder of your day. Again, Skylar, thank you again.